So this is our plan. So let's recap on one page the key elements of electron spin. Electron spin is an intrinsic property of an electron, meaning it's like the mass of an electron, it's like the charge of an electron. These properties are the same no matter where the electron is and no matter in what dynamical states the electron is. It is in sharp contrast to the orbital angular momentum. In an atom, the orbital angular momentum, depending on which orbit it is in, the quantum number L. So S state, L equals 0, it is 0 orbital angular momentum. P state, L equals 1, then it has square root 2 h bar in length of the orbital angular momentum. The second thing is that the spin, given it is half in any projection along any direction, there are only two values. We usually take the direction called Z, and there are two eigenvalues. So these are the two possible components along the Z direction. Usually the Z direction is arbitrary. If there's a magnetic field, then there's a special direction. A convenient choice is to pick that particular direction. Because electron is charged minus E, there is an associated magnetic dipole moment. So with the spin angular momentum, there is a spin magnetic dipole moment. The magnitude of this spin magnetic dipole moment is a constant, square root 3 Bohr magneton. The Bohr magneton is a number that you should roughly remember the order of magnitude. It is 10 to the minus 5 electron volt per Tesla. Spin has two values in any direction, the projection. Therefore, the spin magnetic dipole moment also has two values. It is plus minus Bohr magneton. Okay, so these are the key elements. Last time I also tell you about the breakthrough last year is the muon, which is a constant of the electron in the standard model. So we stopped it there. There are 3 more pages to go, and then we will go into the general angular momentum in quantum mechanics. On these few pages, I just would like to remind you how we could write spin into the wave function within the Schrödinger equation framework. You had that in your previous course last term. It is embarrassment within Schrödinger equation about spin because we have to multiply the spin or by hand add the spin part into the consideration. A full theory with the spin already embedded is a relativistic version of quantum mechanics. It is the Dirac equation of an electron. It is beyond the scope of our course. Maybe I will mention a little bit later, just for cultural purposes, about the Dirac equation. Or I will design a homework problem for you to explore what it is. But it is beyond our scope. Thereby, in our course, we will use the version of Schrödinger wave function and then multiply into it a spin part. So last term, you have solved the hydrogen atom. So this is the ground state 1s, or NLM. Quantum numbers is 1, 0, 0. N is 1, L is 0 is the S state, and there behind L is 0, there's only one M L value, which is 0. which is y00 theta phi, the spherical harmonics, which is just a constant. Now, if we want to describe an electron in a 1s Schrödinger spatial state, and then it is spin up, the way to do it is you have this Schrödinger equation, you multiply into a up spin state. Last term, you learned from Professor Liu that this is a spinner. It's a column with two entries. So this one, if you pick the Z direction as the nice direction, then this is 1, 0. There are many notations of this part. I use alpha, beta for the up, down. I think you used chi Z and chi Z bar in your notes last term. They mean the same thing. Or even you can introduce a fourth quantum number about the Z direction of the spin, just plus half, minus half for the spin up and spin down. Similarly, if it is 1s spin down, then the spin part is 0, 1, or I call it beta, or Professor Liu called it chi Z bar, or else even lazier, there's a fourth quantum number with minus half signaling the Z component of the spin. So there are questions to ask that motivate the next big topics. We are going to discuss spin-orbit interaction. Why we have this idea of spin-orbit interaction? A naive picture will be, let's say, this is the nucleus, hydrogen, this is the electron, it is in a 2p state, for example. L equals 1 is a p state. And we know that there is this non-zero orbital angular momentum. This is the magnitude. According to the Bohr picture, which is not quite right, we can think about the electron is in an orbital motion. So something like a circular orbit. But from your electromagnetism study, you know that an electron going this way is like a current going the opposite way. A current loop will have a magnetic field generated. Thereby, there is a magnetic field that can also apply onto the electron's own spin angular momentum or spin magnetic dipole moment. Therefore, we have this vague picture at this moment that will be expanded further a bit later. So we have this electron orbiting. Thereby, it is like the electron not moving, the nucleus orbiting in the opposite direction. The nucleus orbiting is like a current loop. Therefore, there's a magnetic field at the position of the electron. But the electron also carries a spin magnetic dipole moment. Thereby, we expect to have the interaction between the spin of the electron and the orbital motion of the electron itself. Everything has to do with that single electron. This is called spin-orbit interaction. We will derive, well, 95% of the full expression of the spin-orbit interaction on Thursday. Because the spin and orbital angular momentum will interact, we expect that we better learn how to add them first. Therefore, we are motivated to learn how to add two angular momenta into a new total angular momentum. That will be the topic, part of the topic today. So we are getting prepared to some exciting topics that follows. The first thing I would like to do is a theoretical section. So that is not a section only for atomic physics. It is a big topic in formal quantum mechanics. It is under the topic of angular momentum in quantum mechanics. Realizing that I'm just talking about angular momentum, there's no word in front of it. Therefore, what we are going to discuss should work for, say, orbital angular momentum, spin angular momentum, total angular momentum. When you have 10 electrons in your atom, there will be 10 different orbital angular momentum, and then you have to add them up. So you have a total orbital angular momentum, etc. So what we are going to discuss here should work for anything that will be called angular momentum in quantum mechanics. So it is a very general discussion. So let me motivate it a little bit. In the previous course, you have done orbital angular momentum. And you have seen there are some commutation relations governing the components of the angular momentum. There are some cyclic relationship. Here is one, Lx, Ly. The commutator of them is proportional to Lz with an IH bar in front. You can cyclically rotate these indices, x, y, then the other side is z, or y, z, the other side is x, zx, the other side is y, okay? So there are three of them. And then you also saw this commutation relation of L square commuting with each component. I just write down the Lz here, but it also works for Ly, Lz. There are 6 commutation relations here, all right? And then you work out how to solve the Schrödinger equation, especially the simultaneous eigenstate of L square and Lz. And you have found that there is a set of simultaneous eigenstate called the spherical harmonics. There are very tight criteria for the quantum number L. In orbital angular momentum, L must take on integers, positive. So 0, 1, 2, 3, S, P, D, F, etc. Those states. And given an L, ML also follow very strict rules. It runs from plus L in step of 1. So -1, -1, all the way to minus L. There are 2L plus 1 values of ML. You have seen that, you solve it within the angular coordinates, theta and phi. So you have done this part. Last term, you also did a lot of spin, electron spin. Again, you have seen that there are 6 commutation relations, very similar, just the symbol L become S, otherwise they are identical. So you have 6 identical commutation relations. But for spin of electron, you also know that the quantum number S is always half. And then behind S, there are 2S plus 1. 2 times half plus 1 is 2. Okay, 2 values. And they run from plus S to minus S in step of 1. All right. So for the two angular momenta, you know, there are some common features. They obey the same 6 commutation relations. And then you have seen the quantum numbers, the simultaneous eigenstate of L square and LZ, S square and SZ have some common features. All right. So it's natural to ask the following question. Understand the question first. Our question is, if we only relied on the commutation relations and no more, we just take the 6 commutation relations as the definition of angular momentum in quantum mechanics, the question is, what can we say? What can we say about the eigenstate and eigenvalues of the magnitude square and one component? We usually pick the Z component. So that is the question. So what I mean is the following. Let's take this as the definition of angular momentum, and then ask, for the simultaneous eigenstate of L square LZ, what can we say? All right. Because we want to do something general, we will use the symbol Jx, Jy, Jz, and J square instead of the orbital symbol of L, just to make sure that you understand our result will be general. So we will take this with J as the definition, and then we will work out the general criteria for the eigenvalues and the eigenstate of J square and Jz. All right, so that is the question. Before we go into the operator algebra, I just give you the big picture of the proof so that you can follow the big picture when we go into the details. So basically, the proof will go as follows. We will work out the magnitude square. So there will be some common eigenstates. You see my writing? Of J square and also Jz. Okay. And now, because this is the Z component, this is the magnitude square. The component cannot be longer than the magnitude, right? For any vector. So we will have an inequality to start with about the eigenvalues. Okay, now, at least this is the beginning. Do you understand what this inequality is about? Any question here? Okay. Is that okay? Because that will be very simple, but it is very important. All right. Hello? Nothing's all right? Okay, now, just like what you did in harmonic oscillator physics, we will soon define something called the raising and lowering operator of angular momentum. What they do is the following. Starting with a state with beta, the raising operator will take us to another state from beta to beta plus h bar. Immediately we see the Z component must be in steps of h bar. The next one will be 1 h bar higher, the second one will be 2 h bar higher, and so on. Follow me? So far, so good? Okay. Now then, we will define a lowering operator, J minus. So this is the function of J plus. For J minus, it will take a Z eigenstate into a lower eigenvalue state. Beta minus h bar, minus 2 h bar, minus 3 h bar, and so on. This will be the function of J minus, lowering. All right. Then the key point is, the proof of the key point is the following. Let me see if I can share a sorry, I'm trying to share a whiteboard. Never mind. So with this idea, then you can think about the following. There will be some restriction on the value of beta. Okay. The reason is that if you start at any value of beta, do you see my cross somewhere? Okay. If you keep on operating with the increasing or raising operator, the eigenvalue will keep on increasing. Beta plus h bar, 2h bar, 3h bar, and so on. Okay. But remember, we have this Z component cannot be longer than the vector itself. Sooner or later, this raising operator, if it keeps on increasing the Z component by h bar, it will get to values that are longer than the magnitude of the angular momentum. That will be wrong, right? So therefore, there must be some maximum value of beta. Cut it off. All right. So how can we cut it off? And what is that maximum value? We can derive it. All right. Similarly, you start at beta, you use the lowering operator, it keeps on decreasing the value. All right. Sooner or later, it will be longer than the angular momentum itself. That will be wrong. Therefore, there must be some restriction that can cut it off, stop it. This restriction turns out to be enforcing the maximum value of beta to be equal to the minus of the minimum value of beta. What it means is the following. Let me see. What you see is the following. For L equals 2, the maximum ML is +2. All right. And then you go from 2, 1, 0, -1, -2. The minimum one is -2. Therefore, the maximum one and the minimum one, they are only different by a ± sign. This is what the highlighted part tells us. Understand? All right. Now, we can derive this only relying on the commutation relation. Nothing more than that. We don't need theta phi equation. We don't need YLM theta phi, the spherical harmonics. All right. However, this is not the only option. You see, the other option will be if I start out with 1.5, 3/2 h bar, all right? Minus h bar will be half, minus another one will be -half, minus another one will be -3/2. Good. The maximum one is the negative of the minimum one, all right? You look at this highlighted part on the screen. These are the only two options. What do I mean by that? If you start out with 1.8, do you follow me? 1.8 -1 will be 0.8, -1 will be -0.2, -1 will be -1.2, minus another one will be -2.2. It will go forever. It will be longer than the magnitude of the vector. All right. You see, you start up with 1.2, you will never get to -1.2. Do you see the point? Hello? Hello? Get that? Okay. So therefore, look at this highlighted part. It turns out there are only two options. Either you start with an integer for the maximum Z component, okay? 2, 1, 0, -1, -2. Integer is okay. Another option, half integers are okay. What do I mean by half integer? 1/2, half is okay. 3/2, 1.5 is okay. 5/2, 2.5 will be okay, all right? You cannot find any other numbers that can take you instead of h bar from the positive end and hit at the minus same value. And nature only allows these two possibilities for angular momentum in quantum mechanics. Okay, so this is the take-home message. You follow the derivation, you don't follow the derivation, really doesn't matter. But the result will be very useful for the many discussions to follow. All right, so let me move on. I just would like to check, do you see the whole page? All right. Okay, my device is not working, but my writing device is not working. Okay, so this is what I just tried to tell you. Okay, there are only two options: integer or half integer. So here's the conclusion. I will show you the derivation. All right. It turns out for anything that follows the 6 commutation relations, the magnitude square, J square, the eigenvalue must be of this form. It cannot be any other form. And then this J number, that is the longest component, can only take on either integers or half integers. Okay, you cannot start from 1.2. You cannot start from 1.8. You will not hit minus 1.2 or minus 1.8 in step of 1. Okay, that is spanned by the commutation relations. How nice. All right. And then given the J, the Z component will lower and lower from the maximum value by 1 H bar, and they are all together 2J plus 1 possible values. It starts from J H bar, J minus 1 H bar, all the way to minus J H bar. Okay, now you have seen this in orbital angular momentum. You have seen it in spin half. We are going to prove it generally if we take this 6 commutation relation as the definition, then the general result will follow. So let's start our proof. As we proceed, keep the general picture in mind, okay? Otherwise, you will be lost in some of the algebra. But you have seen that in oscillator physics one time. It's a very similar mathematical trait. So here we start off with, let's say we do have simultaneous eigenstate of J square and JZ. We are confident about this because J square commute with any component, but the components do not commute. Therefore, we have the choice of finding the simultaneous eigenstate of J square and one component. And we usually take it as the Z component, all right? Without loss of generality. So therefore, we say phi is the simultaneous eigenstate of J square and JZ. And then by that we mean J square phi must be a number, which is the eigenvalue times itself. And then JZ, same eigenstate, has the eigenvalue called beta. The game is to find what are the rules governing alpha and beta. So that is the question, all right? The first thing you know by physics is that the magnitude of the vector must be longer than the Z component, all right? So because this is square, therefore, alpha must be bigger than beta square. We will use this later. Then we define two operators from Jx and Jy, which is Jx plus Ijy. We call it J plus. Later on, you will see that it has the function of raising the Z eigenvalue. And another one with minus in between, we call it the lowering operator, the function of which is the lower beta by H bar, all right? At this moment, you have no sense about these two words, but very, very soon you will see it is indeed the case. This is Hermitian, this is Hermitian. This combination is not Hermitian, but don't worry, they are just helping us through the derivation. Then we want to work out some commutation relations. The first thing is, how about J plus J minus commutation relation? That's easy because both are XY. We know XY, the commutation relations, so we can work it out. This means we need to work out J plus J minus and J minus J plus and subtract the result. So let's see. J plus J minus by definition is plus combination minus I combination multiplied together. Immediately you see there is a jx squared term, there's a jy squared term, and then you pick up two more terms. Let me see. So I've seen this one before, but I always unable to understand a different system. Okay, let's hold on to that. And then now you have this cross term, jx, jy, and then jy, jx. That will pick up a commutation relation of jx, jy, and we know that by definition, which is proportional to jz. So the final answer, very important one later, will be this one. J plus J minus is related to jx squared, jy squared, okay, and then h bar j z. Notice that this thing is actually j squared minus j z squared as well, right? Because j squared is defined by jx squared plus jy squared plus jz squared. Okay, so the first two terms can be turned into j squared minus jz squared. That will be a very useful relationship. Similarly, you can work out j minus j plus, follow the same thing. The only difference is this is minus, this is plus, thereby this is a plus, and so on, okay? So you only pick up a different sign. Therefore, the commutation relation will be 2h bar jz. The second commutation relation we are interested in is the following. How about jz, j plus? Easy, definition, plug in, and you know each of these commutation relations by the definition. Therefore, you pick up two commutators, zx and zy, okay? And then it turns out that you get h bar j plus. Similarly, jz j minus is minus h bar j minus. All right. So these two will be used to prove the function. What does it do? That j plus will raise the z eigenvalue, and minus will lower the z component eigenvalues. Next, we will see what do these two things actually do. So now we operate j plus onto our simultaneous eigenstate and then test whether this, after operation, which is a new function, so after operation, which is a new function, we want to test whether the new function is still an eigenstate of jz. Okay, so do you understand why we write down the left-hand side? Now let me repeat. Now this is the simultaneous eigenstate we assume. We operate j plus on it, which will give us a new function. We want to test whether this combination, this new function, is again an eigenstate of jz. Therefore, we want to play with jz, this new function, and see whether it comes out as a number times this new function. All right. Now, jz j plus. Use this one. Okay. jz j plus will be this one, okay? So JZ J plus equals J plus JZ plus H bar JZ. All right. So therefore, we have this line. And now, by definition, JZ phi is beta phi. All right. And beta is a number that will pass through the J plus operator. JH bar H bar J plus. This one. Right. Okay. So after you operate JZ on this phi, a beta will come out and left you with J plus phi. Therefore, in both terms, you have J plus phi factoring out. Indeed, now JZ, this new function, is a number, the same new function. Okay, that proves the following. If phi is an eigenstate of JZ, J plus phi is also an eigenstate of JZ with a new eigenvalue, which is 1 unit of H bar higher than beta. Okay. Similarly, you can prove J minus phi is also an eigenstate of Z component with a new eigenvalue, which is minus H bar lower. That gives us the name. J plus is the raising, J minus is the lowering operator, angular momentum sense. So in summary, J plus phi is also an eigenstate of JZ, but now eigenvalue is 1 unit H bar higher. J minus is 1 unit minus H bar lower. All right. So this is the most important effect. Next, we want to also check after we operate J plus J minus on the simultaneous eigenstate, will it change the magnitude square eigenvalue, which is called alpha here? All right. The answer is no. Let me show you that. J square J plus commutator is 0. The reason is that J square commute with any component. J plus J minus are made up of linear combination of the components. Therefore, they are commute. All right. Therefore, when you have this, you want to test whether J square, whether that combination, that new function is still an eigenvalue of J square. You do this, you can flip the order because they commute, and you pick up an alpha in this combination, which is just an eigenvalue, a real number. You can pick it out in front. Therefore, this new function is an eigenstate of J square with the same eigenvalue alpha. That is to say, J plus will not change the magnitude of J square. It remains in that same J square multiplet, so-called. Similarly for J minus. So conclusion in the box, J plus J minus cannot change the eigenvalue of alpha. All right. So now we have this situation as I already explained in the big picture. We have a criteria. The Z component cannot be longer than the magnitude of the vector. But then we have a J plus keep on raising the eigenvalue. If we don't stop it, we will run into trouble. Therefore, there must be a maximum state that I call phi maximum, corresponding to the highest possible reset component. After that, it cannot be raised anymore by J plus. Okay? How to stop it? We must require when J plus operate on this maximum reset component eigenstate, it stops 0. Once it satisfies this, further operation of J plus will remain 0. Therefore, the eigenvalue will stop at some beta maximum and never go beyond the length of the vector. So equation 14 defines the highest reset component eigenstate. It must satisfy this equation. All right. Now, similarly, we can cut off the lower one. So you have a maximum reset component, then you have a minimum reset component. J minus keep on decreasing the eigenvalue. We don't want it to go non-stop. That will be wrong because it will be longer. It will be longer than the vector itself. So some minimum reset component state must exist such that when J minus hit at this state, it stops 0. Once you have this 0, you operate J minus on it, it will keep on giving you 0. It will not go lower and lower and lower in eigenvalue. All right. So we are getting there. We defined it the maximum one and the minimum one. All right. The next step we call, when we do the commutation relation, we have these relationships. Okay. We will be using it now. So, by definition, there's a maximum reset component state. When I operate J plus on it, it stops 0. Okay? Now, I operate J minus. Now, I start from the maximum one. I can lower it, right? That's fine. But since this is J minus operate on 0, it should be 0. All right. However, we also know that J minus J plus is given by this one. All right. So I copy this through. Then I have a very interesting relationship. J square operate on the maximum one. We know that it will not change alpha. So it's just alpha, the same state. J Z square on this maximum component projection, Z component eigenstate will give us beta maximum square. J Z on this will give us beta maximum the state. All right. So do you see how I get this thing from the upper line? There are 3 operations. J square on it, we prove it, it will stay at alpha. J Z on phi beta maximum is beta maximum times the state. It is the eigenstate. J Z square means operate another J Z. So you pick up another beta maximum. You have beta maximum square. Do you see that? However, this whole thing must be 0. The state is not 0, so this bracket must be 0. So we have a relationship. The magnitude square eigenvalue must of this form. All right. Now I can play with the lower end. I also cut it off at the lower end with a minimum state. I operate J plus on it. Same thing. Then I got this requirement. All right. Now you compare this with this. Compare this with this. All right. If you cannot immediately see it, how about writing it this way? The right-hand side minus beta maximum minus beta maximum minus H bar. Do you agree that it is just the same as equation 16? Right? Now you compare this with this. Same form, right? Therefore, from the reason the Z component cannot be longer than the magnitude of a vector, now there's a restriction. The maximum value of the Z component must be related to the minimum value of the Z component. They are off by a minus sign only. All right? Get me? So we get at what we claim in the big picture. All right? So you have seen this before in different contexts. You have seen it in orbital angular momentum. For D state, L is 2. The projection Z component, biggest one is +2. Smallest one is -2. They are in step of 1 H bar, 2 H bar, 1 H bar, 0, minus H bar, and -2 H bar. So you have seen this case, maximum and minimum off by a sign. Okay? So that takes us back to the same picture. Here, okay, on the previous page. What we got is that the maximum value and the minimum value must be off by a sign only, like plus something, minus something, okay? And there are only two possibilities in mathematics that can be the case. Either it is an integer, the maximum value is an integer H bar. Instead of H bar downward, you will hit minus the same integer H bar. Or else, you start with a half integer, 5/2, 7/2, 3/2, okay? You use J minus take you down, and you will hit a minimum that is the same number with a minus sign. All right? Now, if you start off somewhere, for example, here, let me see, 0.8, -1, okay? 0.8 minus 1 is what? Here, -0.2, -1.2, -2.2, -3.2, -4.2. You will never hit at the negative number of what you start off with, all right? So the conclusion is that beta maximum can only take on two types of numbers: integer times H bar or half integer times H bar. So let me go back to that page. So the maximum value, the Z component can either be integer H bar or half integer H bar. Okay? So now we will switch to the proper notation. We will say the maximum value is a JH bar. The minimum must be minus JH bar. J can be either integer, 0, 1, 2, 3, positive, or half integer, half, 3 half, 5 half, etc. These two possibilities are allowed by the 6 commutation relations. Once you have J given, okay, the Z component will take on 2J plus 1 values because they are in steps of 1 H bar apart. Okay, so there are 2J plus 1 values. Finally, how long is the J square eigenvalue? Remember, we proved that it must be J maximum plus H bar. J maximum is JH bar, therefore, we have our familiar form. Okay, let me conclude and then we will take a break. Conclusion. Based on the 6 commutation relations only and nothing else, we have not used any so-called representations. We are not doing it in theta phi space or any other space, just 6 commutation relations. It turns out that there are very stringent conditions on the simultaneous eigenstate of J square and JZ. J square must have eigenvalues of this form. And this quantum number J is restricted to take on either integer, positive, or half integers, positive. All right? And now, given a J, JZ can go from the longest one, maximum one, to a minimum one, which is negative J, H bar, instead of H bar, because of this raising and lower operator functions. Okay? So this ends the proof. See? Nothing fancy. 6 commutation relations. This box is the general result for angular momentum in quantum mechanics. So let's take a break. We will come back and then kill off the remarks. The remaining pages are remarks of this general result.